No aircraft in the history of aerial warfare has more documented its own invulnerability and its own vulnerability than the Boeing B-17 Flying Fortress. The 8th Air Force flew it into defended airspace where loss rates of 25% per mission were recorded. It returned from those missions with engines on fire, tail surfaces destroyed, and crew dead at their stations. The engineering decisions that made survival possible were not considered the aircraft's strengths when Boeing's design team made them. They were considered its flaws. What those flaws did and why they worked is what the official damage reports record. In August 1934, the United States Army Air Corps issued a design requirement for a new multi-engine bomber. The specification asked for an aircraft capable of carrying a 2,000-pound bomb load to a target 1,020 miles distant at a cruising speed between 200 and 250 miles per hour. The requirement specified multi-engine without specifying a number. 3 of the 4 manufacturers who responded read that as 2. Boeing read it as 4. The aircraft Boeing submitted for evaluation, designated the Model 299, used 4 Wright RIAR 1820 Cyclone radial engines, producing a combined output of 3,040 horsepower. It weighed 38,000 pounds fully loaded. The next heaviest Douglas competitor weighed 27,000 pounds. Boeing's engineer, Edward C. Wells, had understood the specification as primarily a survival problem. The number of engines was his answer. The structural philosophy Wells encoded into the Model 299 was not standard for the period. Military aircraft of the early 1930s were built to a load factor of approximately 150% of the calculated flight load. Wells specified 150% as the floor, not the target. Every primary structure was calculated to survive loads that routine flight would never impose, emergency maneuvers at maximum weight, partial structural failure redistributing loads onto intact members, and the forces of battle damage. The practical consequence was an aircraft whose wing spars, fuselage frames, and control system components were heavier than a straight performance calculation required. The practical consequence in combat was an aircraft that remained flyable after the specific failures that German cannon shells would routinely cause. Wells was not designing for routine flight. He was designing for the flight home. USAAC procurement officers at Wright Field evaluated the Model 299 against the Douglas DB-1 and Martin 146 through autumn 1935. The Boeing aircraft was faster, a maximum speed of 252 miles per hour at 10,000 feet against the DB-1's 200, and its range was substantially greater. Procurement evaluators recorded their concern about the Model 299's weight and cost, alongside their admiration for its performance. Boeing was building a more capable aircraft than the specification required. That capability came at a price that Army budget officers found difficult to justify in peacetime. The word used in the evaluation correspondence was excessive. It would be used again by different officers in 1940 and 1941 as Boeing continued adding systems to subsequent variants. The word would not appear in post-mission damage assessments after 1942. On 30th October 1935, with the evaluation nearly complete and Boeing holding a clear performance lead, Major Ployer P. Hill of the USAAC and Boeing test pilot, Leslie Tower, took the Model 299 up from Wright Field for a final evaluation flight. The gust locks, devices that immobilize the control surfaces on the ground to prevent wind damage, had not been disengaged before takeoff. The aircraft climbed, reached 300 feet, lost control authority in the locked surfaces, and stalled. It crashed and burned on the field. Major Hill and Tower died of their injuries. The Army Air Corps awarded the production contract to Douglas. Boeing salvaged the program by producing 13 YB-17 service evaluation aircraft at its own cost, without a production contract. The 13 YB-17s entered service evaluation with the 2nd Bombardment Group at Langley Field, Virginia in 1937. The crews who flew them across the United States, over the Atlantic, and on navigational exercises in South America filed reports that were consistent on one point. The aircraft was unusually tolerant of the kind of systems failures that would have forced a twin-engine crew to emergency procedures. Engine failures during training missions, routine events in an era of high-maintenance radial engines, produce nothing more serious than a gentle asymmetric correction and a completed mission. The four-engine redundancy Wells had specified in 1934 was already doing what he had specified it to do. The USAAC procurement officers were not paying attention. The engineering department at Boeing Plant 2 Seattle in the early weeks of 1934 occupied a floor of drawing tables under incandescent lights. Edward C. Wells, 22 years old and recently out of Stanford, sat at a drafting board near the east windows. In front of him was the preliminary weight estimate for the Model 299 with 3 engine mounts specified. The range calculation worked. The speed calculation worked. The weight was within procurement limits. He had a viable aircraft on paper. He added a 4th engine mount. The additional weight was 820 pounds. The range calculation still worked marginally. The speed was reduced by 4 miles per hour. He left the change in the drawing. The reason he left it was not recorded in any specification document. It was the calculation he had run the previous evening, the probability of an aircraft losing one engine at maximum range over open water, and the arithmetic of what happened to the remaining crew with 2 engines versus 1. The 4th engine mount stayed in the drawing. The B-17B entered service in 1939 with 9 .30 caliber guns and a single 50 caliber weapon in the nose. The B-17C and B-17D, delivered to the USAAC in 1940 and early 1941, added self-sealing fuel tanks, a modification driven by RAF combat experience reports from the European theater, where fuel fires had destroyed numerous aircraft from incendiary rounds that would not otherwise have been fatal. The Goodyear-developed rubber tank lining added 350 pounds to the aircraft. USAAC program managers questioned the weight penalty. The argument in the modification order was the same Wells had made with the 4th engine in 1934. The weight is the cost of not burning. The modification was approved. By 1941, the B-17E had added a tailgun position, a dorsal turret, and a ventral ball turret. The B-17G, the final and definitive production variant, which entered service in September 1943, carried 13 Browning M2 .50 caliber machine guns, operated by a crew of 10. It weighed 135 pounds empty and 65,100 pounds fully loaded for a combat mission. Procurement officers had been making the same calculation for 9 years. The aircraft was heavier than it needed to be, costlier than it needed to be, and demanded more trained crew than any equivalent mission required. Each of those objections was accurate. None of them accounted for the condition the aircraft would be in when those 10 crew members needed to bring it home. The weight they were carrying was not excessive. It was structural margin, redundant systems, self-sealing tanks, and defensive armament accumulated over 9 years of incremental decisions by men who understood that a bomber that cannot return is not a bomber. The B-17 had been built exactly as Wells and his team had intended. The over-engineering procurement officers had been noting in their correspondence since 1935 was not a design error that had somehow escaped correction across 9 years. It was the design. What that design would do when the 8th Air Force began flying it from eastern England in 1942, and what German fighter pilots would do when they encountered it above the Reich, was something the aircraft structure had been calculated for since a drawing board at Boeing Plant 2 in Seattle 8 years earlier. The defensive armament that determined how survivable that structure could be was still being built in increments. The specific problem it was designed to solve was about to be precisely identified by the Luftwaffe. The B-17E, which began arriving at 8th Air Force bases in England in the summer of 1942, was substantially different from earlier variants. Boeing had responded to combat reports from the RAF and from early USAAC Pacific operations by adding three gun positions that all previous variants had lacked: a dedicated tail gun position operated by a rear gunner, a Bendix dorsal turret carrying twin 50 caliber Browning M2 machine guns above the cockpit, and a Sperry ball turret suspended beneath the fuselage. The aircraft arriving at Polbrook and Thurley in 1942 was not the bomber Wells had drawn in Seattle in 1934. It was a machine whose every external surface pointed a gun outward. The Luftwaffe would spend the next year finding the angle from which that was least true. The first 8th Air Force raids against targets in France and Germany in the autumn of 1942 established the basic tactical pattern. B-17 formations flew at altitudes between 20,000 and 28,000 feet in tight box formations that generated overlapping defensive fire from multiple gun positions. German fighter units that attempted conventional stern or beam attacks found themselves flying into sustained .50 caliber fire from ball turrets, waist guns, and tail positions for the full duration of their firing run. Losses were unsustainable using those vectors. By November 1942, Luftwaffe fighter controllers had gathered sufficient post-mission debriefs to establish a consistent pattern. The B-17's defensive coverage had significant gaps on only one approach axis. German pilots who had identified it were filing the same observation. The nose of the aircraft was under-defended. The officer who systematized the solution was Oberst Egon Mayer, commanding the 3 JIS 2 at Van in Brittany. Mayer had mapped the B-17F's defensive coverage arc at every degree of the compass and found the one angle where a fighter could close to firing range with minimum exposure time. Head-on, slightly above and to the right, at combined closing speeds of approximately 500 miles per hour. At 12 o'clock high, the B-17F's nose gunner had less than 3 seconds to acquire a moving target. The B-17F's nose weapons were handheld 30 caliber cheek guns with limited traverse arcs. Neither condition favored the defender. The same maneuver also reduced total exposure time to defensive fire from adjacent aircraft in the formation. Mayer codified the attack geometry and distributed it to Luftwaffe fighter units across occupied France in the winter of 1942 to 1943. The frontal attack became the standard Luftwaffe tactic against B-17 formations throughout the first half of 1943. Its effectiveness was measurable. Post-mission assessments from 8th Air Force intelligence officers showed that battle damage to the nose section, forward of the cockpit, was more frequently fatal to aircraft and crew than equivalent damage elsewhere. A 30 caliber weapon operated through a small aperture was inadequate defensive armament for an approach vector closing at 500 miles per hour. The B-17F's crews were aware of the problem. Group commanders were filing reports by February 1943. The question reaching Boeing's Seattle facility was not whether the nose was inadequately defended. It was how to add the required firepower without exceeding the airframe's load capacity. A Luftwaffe briefing room at Van, Brittany, in mid-December 1942. Oberst Egon Mayer stood before his pilots at a table, a hand-drawn diagram of the B-17F's defensive coverage arcs chalked onto the blackboard behind him. The arcs were dense everywhere except directly ahead. There was nothing there at all. He had placed a chalk mark at 12 o'clock. The chalk mark was the nose of the aircraft. He explained the physics: a head-on pass at 500 miles per hour. Closing speed gave the bomber's nose gunner less than 3 seconds to acquire a moving target. He explained what the pass required of the pilot: full combat throttle, a diving approach from above the formation, and the nerve to fly through the B-17s rather than break off short. The pilots in the room had spent the autumn attacking from the rear. They had the loss figures in their heads. He pointed at the chalk mark again. He put the chalk down, They had been attacking the correct aircraft. They had been doing it from the wrong direction. The combat box formation was the 8th Air Force's answer to the fundamental problem. Individual B-17s were vulnerable, formation B-17s were not. The geometry was developed by multiple group commanders during 1942. The 305th Bomb Group under Colonel Curtis LeMay at Chelmsford was credited with the most rigorous formalization of the doctrine by December 1942. A combat box arranged between 18 and 36 aircraft in staggered altitude positions, high, low, and lead elements, so that any fighter attacking from any direction but directly ahead faced defensive fire from multiple aircraft. The innovation was not the formation itself. It was the calculation of the specific positions required to ensure no blind spot existed from any approach angle except the one Mayer had already identified. The combined firepower of a full combat box was not an abstraction. A 36 aircraft wing carried 468 50 caliber Browning M2 machine guns, 13 per aircraft, generating at medium cyclic rate approximately 5,850 rounds per second. A German fighter approaching from any defended angle was flying into a volume of fire that no single aircraft could survive intact. The formation was self-reinforcing. More aircraft meant fewer survivable attack vectors. The aircraft that generated that firepower, by carrying all those guns, all that ammunition, and the 10-man crew required to operate them, was the aircraft that procurement officers had spent 9 years calling too heavy. They had been correct about the weight. They had been wrong about what the weight was for. The B-17G, which entered service in September 1943, addressed the frontal attack problem with a Bendix chin turret mounted below the nose, carrying twin 50 caliber machine guns in a power-driven mount. The chin turret was the engineering response to Mayer's frontal attack geometry. It added weight, approximately 250 pounds, for the complete installation. It closed the one defensive gap that head-on attacks had been exploiting for 9 months. Mayer, who had systematized the attack, was killed in aerial combat over Normandy on 2nd August 1943, 6 weeks before the B-17G entered service. Luftwaffe units continued developing the tactic. The B-17G's chin turret made it more expensive to execute. The head-on attack remained standard because no approach was cheap. The B-17, the 8th Air Force flew into Germany in the second half of 1943, was a different machine from the one Wells had drawn in Seattle in 1934. It was heavier, more heavily armed, more expensive to build, and demanded more trained crew than any equivalent bomber program. The procurement officers, who had been noting this in their correspondence since 1935, were still writing the same observations in 1943. The word excessive had not been withdrawn. What had changed was the operational context. The 8th Air Force was now flying 200 and 300 aircraft at a time into the most heavily defended airspace in history, against a German fighter force that had identified the one remaining exploitable weak point in the B-17's defensive geometry and was attacking it systematically. What happened to those aircraft above Schweinfurt and Regensburg, what the aircraft survived and what it did not, is documented in the post-mission damage reports the 8th Air Force filed at its Eastern English airfields between 1942 and 1945. The 8th Air Force flew its first bombing mission from England on 17 August 1942, 18 B-17Es against the Rouen-Saudeville marshalling yards in occupied France. None were lost. The mission established a pattern of early optimism that the 8th's commanders would spend the next 14 months systematically revising. As missions penetrated deeper into Germany, beyond the range of P-47 Thunderbolt escorts that could accompany formations only to the Dutch border, loss rates climbed in direct proportion to the time spent unescorted. A mission to a target in France cost on average between 1 and 2% of committed aircraft. A mission to the heart of central Germany cost between 8 and 12%. The arithmetic of sustained deep penetration operations was not sustainable. The clearest evidence arrived on 17 August 1943. The 8th Air Force dispatched 230 B-17s against the Messerschmitt factory at Regensburg and the ball-bearing plants at Schweinfurt. Two targets struck simultaneously to split the German fighter response. 36 were shot down over Germany. A further 27 were so severely damaged they never flew again. The effective loss rate was 27.4% of the committed force. The mission demonstrated both the B-17's survivability and its vulnerability. Of the 167 aircraft that returned, most carried battle damage that would have destroyed a less robust aircraft. Of the 63 that did not return, the structure Wells had specified in 1934 had not been sufficient to overcome unescorted flight over a concentrated fighter defense. The aircraft had performed as designed. The doctrine had not. The second mission to Schweinfurt was flown on 14th October 1943, Black Thursday. The 8th Air Force dispatched 21 B-17s. 77 were shot down. A further 121 returned damaged beyond immediate flight. In a single afternoon, 650 crewmen were killed, wounded, or captured. The effective loss was 26.4% of the dispatched force. The 8th Air Force stood down from deep penetration operations for 3 weeks. The Schweinfurt losses were not a failure of the B-17. The aircraft had absorbed the damage that came its way and returned in numbers that no other bomber in the Allied inventory would have matched. The failure was the absence of the one thing the B-17 could not provide for itself: an escort fighter with the range to stay with the formation throughout the mission over Germany. The post-mission damage assessments established a finding that complicated the prevailing narrative about B-17 survivability. Approximately 7% of B-17 combat losses between 1942 and 1945 were attributable to anti-aircraft artillery, flak. Fighter attack accounted for approximately 23%. The defensive architecture Boeing had built and the combat box formation designed around it was effective against fighters. It addressed approximately 23% of the total threat. The majority cause of loss was a weapon that no formation geometry and no defensive gun turret could counter. An 80 mm shell detonating within lethal radius of the fuselage. The B-17 had been designed to survive a specific problem that was real and well-defined. The problem it could not survive was the larger one. The documented cases of B-17s returning from missions that should have destroyed them exist in sufficient number to constitute a category. On 1 February 1943, a B-17F of the 97th Bomb Group, designated All-American, was struck over Tunisia by a German fighter in a ramming attack that nearly severed the rear fuselage from the aircraft. The tail section was held by structural connections, a section of spar, and several control cables. Lieutenant Kendrick Bragg flew the aircraft 70 miles to base at reduced speed, the tail flexing with each air movement. The aircraft landed. The tail collapsed on the runway during rollout. All crew survived. The post-mission photographs of All-American show the spar wells had overspecified in 1934 still intact at the fracture point. The Flaw held, a dispersal hardstand at Thurley Airfield, Bedfordshire, in the autumn of 1943. A B-17F had returned from a mission to a target in the Ruhr. The aircraft had landed under its own power with 2 engines feathered and one wheel of the main landing gear partially collapsed. The maintenance crew chief stood at the nose with a hand counter and began walking the perimeter of the aircraft, inserting a wooden rod into each flak hole to confirm the penetration was through the skin. He walked the length of the fuselage on the left side, the tail section, the right side, and back to the nose. He did not count wing root damage separately. He pressed his counter 127 times. One waist gunner had been killed at his station. The oxygen system had been perforated. Both inboard engines were operable but running outside temperature tolerances since the target. He wrote the penetration count in his maintenance log. He did not annotate it as exceptional. It was Thursday. This was what Thursday looked like. The damage data pointed to a distinction that was not being made clearly. Aircraft that failed to return were not aircraft destroyed by a single catastrophic hit. They were aircraft that had sustained cumulative damage beyond the threshold at which four engines and redundant systems could compensate. The B-17 did not survive because it was invulnerable. It survived because Wells had calculated the probability of specific failures and built the margin to continue flying after those failures. An aircraft that lost one engine and had self-sealing tanks had a chance of returning. An aircraft that lost two engines and took a flak hit in the fuel system did not. The over-engineering set the survival threshold. It did not eliminate it. The solution to the escort range problem arrived in January 1944. The North American P-51B Mustang, fitted with drop tanks and powered by the Rolls-Royce Merlin engine, could escort B-17 formations from England to Berlin and return. The first P-51 escorted raid to Berlin was flown on the 4th of March 1944. The effect on 8th Air Force loss rates was immediate and permanent. The average per mission loss rate for B-17s fell from approximately 3.5% in the final quarter of 1943 to approximately 1% by mid-1944. The B-17 that Wells had designed as a survivor had been flying into conditions that required it to survive alone. The P-51 removed that requirement. The full record of what the 8th Air Force documented in post-mission damage assessments, aircraft by aircraft, mission by mission, is held at the Air Force Historical Research Agency, Maxwell Air Force Base, Alabama. The Boeing engineers in Seattle never saw those reports. What they established about why the aircraft survived is the engineering question this account has begun to answer. The 8th Air Force lost 4,145 B-17s in combat between August 1942 and May 1945. It dispatched 291,508 sorties and delivered 640,036 tons of bombs onto European targets in the same period. That ratio was the operational result of a design philosophy Wells had encoded at Plant 2, a decade before the first B-17 crossed the English Channel. The aircraft had survived what it was built to survive. It had not survived everything it encountered. The engineering question, why the margin Wells built in, produced the specific survival outcomes recorded in those post-mission damage assessments, is a question about materials, systems redundancy, and structural mechanics. The answer, worked out painstakingly by USAAF engineers examining returned aircraft at English bases between 1943 and 1945, is what this account now examines. The 8th Air Force's operational records arrived at Maxwell Air Force Base, Alabama, in the months following the German surrender of May 1945. The collection included post-mission damage assessments filed at every 8th Air Force base in England, one for every aircraft on every mission between 1942 and 1945. A USAAF officer worked through a sample of those records in the summer of 1945. His calculation was specific: the relationship between engines lost and return probability by aircraft type. He ran the numbers separately: first twin-engine aircraft, then four-engine. He set the twin-engine results aside. He put the four-engine results in front of him and carefully read through them a second time. An aircraft with four engines that lost one had a return probability of approximately 94%, controlling for the type of additional damage sustained. An aircraft that lost two had approximately 75%. A twin-engine aircraft that lost one engine had approximately 47%. He wrote in the margin of his calculation sheet, "The fourth engine is not redundancy. It is the mission." The probability mathematics of four-engine survivability were not complicated once the data existed to run them. An aircraft with four engines generating equal thrust loses 25% of its power output when one engine fails. It retains directional control, it retains altitude holding capacity, and it retains the ability to complete the mission at reduced airspeed. An aircraft with two engines loses 50% of its power output on a single engine failure. At combat weight, 1,500 pounds fully loaded in the B-17G, a 50% power reduction produces an aircraft that cannot maintain altitude, cannot complete the mission, and faces the return flight at a reduced speed that extends total exposure time over defended territory. Wells had not specified 4 engines because he anticipated losing one as a routine event. He specified 4 engines because he understood that over a campaign of hundreds of sorties, the probability of any given aircraft losing one engine was not negligible. The redundant engine was not a luxury. It was an actuarial decision. The self-sealing fuel tank addressed a different probability. An incendiary round, 7.92 mm or 13 mm from German fighter weapons, 20 meters from Luftwaffe cannon, that penetrated a standard fuel tank produced one of 2 outcomes. The round passed through without igniting the fuel, or it did not. When it did not pass through cleanly, the result was a fuel fire that typically destroyed an aircraft in less than 90 seconds. Goodyear's rubber vulcanization process, adopted for the B-17C in 1941, produced a tank lining that swelled when contacted by aviation fuel, sealing a penetration before combustion could establish. The weight penalty was 350 pounds. The question Wells and his team faced was whether 350 pounds was too much to add to an aircraft already criticized as overweight. The answer they reached was the same one they had reached with the 4th engine. The 350 pounds was not a cost. It was the alternative to burning. The structural redundancy carried its evidence in the All-American case and in dozens of similar documented returns. The critical mechanism was the multi-spar wing and fuselage design. Standard aircraft construction of the period typically employed a single primary spar per wing, with secondary structure to distribute load. Wells specified a multi-spar design in which the primary load path was duplicated so that partial failure of one spar redistributed load onto the intact secondary members rather than precipitating catastrophic structural failure. The All-American's rear horizontal stabilizer spar fractured completely in the ramming collision over Tunisia. The forward spar and the control cables held. The geometry of the tail structure changed. The flight characteristics changed. The aircraft remained flyable. A single spar stabilizer would not have produced the same outcome. The overspecification that added weight and cost to every B-17 produced in that specific case the difference between a crew that returned and a crew that did not. The doctrine that required the B-17 to fly straight and level at predictable altitudes into defended German airspace was not a military error improperly understood. Precision daylight bombing was demonstrably more effective at destroying specific industrial capacity than area bombing conducted at night. The ball-bearing plants at Schweinfurt, the oil refineries at Ploesti, the aircraft factories at Regensburg, these were targets that required precision, and precision required daylight, and daylight required surviving the anti-aircraft and fighter defense that German commanders concentrated around them. The B-17 was the platform that absorbed the tactical cost of the correct strategic theory. A less structurally robust aircraft, one that procurement officers had allowed Wells to build to weight and cost, rather than survival margin, would have imposed a loss rate at which the 8th Air Force's deep penetration campaign would have ceased to be operationally viable before the P-51 arrived. The aircraft bought the time the doctrine needed. What the over-engineering actually cost was straightforward to calculate. Each B-17G weighed approximately 6,000 pounds, more than the minimum structure required to carry its bomb load and crew to target and return under ideal conditions. That 6,000 pounds represented reduced bomb capacity, reduced airspeed, and increased manufacturing costs per aircraft. What it produced, quantified in the damage assessments that filled the shelves at Maxwell, was a return rate from heavily damaged missions that no other bomber design achieved. Between 1942 and 1945, 8,500 M86 B-17s returned from combat operations. A significant fraction of those returns, the aircraft that came back with two engines feathered, with tail sections structurally compromised, with fuel systems penetrated and sealed, were returns that the weight penalty had purchased. The procurement officers were right that the aircraft was heavier than it needed to be to fly the mission. They were measuring the wrong thing. The weight was not the cost of flying the mission. The weight was the cost of surviving it. None of that was what Wells had been trying to prove in 1934. He was not writing a manifesto about over-engineering as a design philosophy. He was answering a specification. The specification asked for an aircraft capable of carrying a bomb load to a defended target and returning. Wells read that as a survival problem and designed accordingly. The four engines, the structural margin, the redundant systems that procurement officers spent a decade calling excessive, each was the specific engineering answer to a specific sub-question within that larger problem. How do you continue flying when you lose an engine over the North Sea? You have three more. How do you prevent a fuel fire from an incendiary round at altitude? You seal the tank before combustion establishes? How do you fly home when a German fighter has fractured your rear spar? You designed a second load path, 10 men at a time, on two 91,108 sorties over 3 years, discovered whether those answers were correct. The engineers in Seattle who specified the Model 299 in 1934 were solving a procurement requirement. The four engines were required because the specification demanded range. The heavy structure was required because the specification demanded survivability at altitude. The self-sealing tanks were added because the specification demanded operational viability over defended territory. No engineer wrote in the margin of a drawing, "This aircraft will bring young men home from missions that should have killed them." That was not in the specification. What was in the specification, correctly understood, was a machine designed to absorb punishment without surrendering its crew. The engineers had done their work. Between 1942 and 1945, 10 crewmen at a time found out whether the work was sufficient. Most of the time, against all expectation and against the weight of probability, it was. The over-engineering was never a flaw. It was the point.